All right, next we have example 3, which is to find, or how to find a potential function given a vector field. So in this problem in particular, we want to first show that f is conservative and then find a potential function. In general, it's always good to make sure something exists before you go looking for it. So if we're going to spend some time trying to find this scalar function f, we want to make sure that it's actually out there, because we may otherwise be looking for a very long time, or more realistically, you may run into some algebraic issues and get confused as to why these issues are occurring. Well, it's probably because the vector field isn't conservative. Some problems, they will specifically ask you to show that it is and then find one. Some problems might be a little bit more open-ended and phrased in such a way that it says show that, find a potential function for f or state that one does not exist. Something like that. So let's go ahead and find a potential function. So to find a potential function, what we're going to do here, since this is a two-dimensional vector field, what we want to end up doing here is taking a look at the above condition where we have a two-dimensional field, so it's only this. We don't have to worry about the other conditions, and we can't take the curl of a two-dimensional vector field. So there's no z, so all that stuff is gone, and we're just verifying this. So del f2, del x, that is the x partial of the second component of the vector field, which is 2x plus 3y squared. And then we have the del f1, del y, the y partial of the first component, which is 2x plus 3y squared. These are equal, so this tells us f is conservative. Check. And therefore, there exists a potential f such that the gradient of little f equals big F. So that's the first part. We have shown that the vector field is conservative, and this little extra statement here is telling us sort of what we're going to do next. Because the vector field is conservative, what's conservative mean? Conservative means this. So this tells us there is such a function f, little f, whose gradient equals the vector field. Because this vector field is two-dimensional, that means our scalar potential function, little f, has to be a function of two variables, x and y. So remember, what is the gradient of a function of two variables? Well, it's the x partial derivative and the y partial derivative. And then we know what our vector field f is. That's 2xy plus y cubed, comma, x squared plus 3xy squared plus 2y. So because of this, now we can do the following. This is a vector equation. So this first component has to equal that first component. So let's go ahead and start there. So I'm going to start this process sort of in the next little place here. Just so we have some room. So because this first component has to equal, this first component, we can go ahead and set them equal. So f sub x, the x partial derivative, is equal to 2xy plus y cubed. Well, our goal here, let's write this down here. What's our goal? find f. Well, right here, we don't have f, but we have the x partial of f. How can we go from the x partial derivative of something back to that original something? Well, we'd have to undo the x derivative. How do we undo an x derivative? With an x integral. So if we integrate both sides with respect to x, we should get back f. So integrating with respect to x, we should get x squared y plus xy cubed. And now you may be very tempted to go ahead and write a plus c here, because that's what you do in Calc 1. When you do a definite integral, you have to account for any constants that could have been there. Because if we have any real number here, right, if I have the number 17 here, well, clearly if I differentiate it, that 17 goes away, and that's why there's nothing here. But that number could also have been, negative pi to the e. But its derivative is also 0, that's why it doesn't show up here. So we have to account for anything that would vanish upon differentiation. And in Calc 1, there's only one variable. So the only thing that does vanish with differentiation, with respect to your one and only variable, it has to be a constant. But because we're in multivariable calculus, we have more than one variable. And right now, this is an x integral. So all we have to make sure of is that whatever we put in this red box, whatever goes here, we just have to make sure that when we take the x partial derivative of this, it equals 0. So sure, we could put plus c in the box, right? That would work. But it would also be okay if we had like the natural log of y. Sure, y is not a constant, but with respect to x, it is a constant because x and y are independent of one another. X can be whatever it wants to be, and y can be whatever it wants to be. The value of x does not influence the value of y, so they don't depend on each other. So they're constant with respect to one another. So really, we can include anything that's not the variable that we integrated with respect to. So how do we encode that? Well, we're going to put in this box here a function of y. Really, this just is a placeholder for anything that contains y's or real numbers. It's just a placeholder. So this is basically saying some math expression with y's. That's really what it's saying. So right now, this gives us an expression for f. Is it perfectly concrete? No. Because although these first two terms are tangible, this one is sort of ambiguous. We don't really know what this is. We just know that whatever goes here, as long as it contains numbers and y's, then if we differentiate it with respect to x, we would still get back this, which is really all we're trying to ensure happens. We just want to make sure that if we differentiate this with respect to x, that we do actually get this. So it could be y's, could be numbers, can't be x's. All right. So basically what we've done, if we think of this like big picture, we had nothing. We knew nothing about f in the beginning. But using this equation right here, we were able to say, okay, but we know what the x partial is. And from there, we were able to recover some additional information about f. It's not perfectly known, but we at least know that f has to contain these two terms, and it could possibly contain other things. So in a sense, we have refined our answer. We went from knowing nothing about f to knowing a bit more about f. And now what we're going to do is refine again. Because what piece of information have we not yet used? we haven't used the fact that the y partial derivative of f is this component. So now we're going to do a second round of refinement. So maybe we'll just section this off. That was round 1 of refinement. Round 2, we're going to go ahead and take the y partial of this expression. Why would we do that? Well, because we know that the y partial of this expression, because this expression is just f, so we know that the y partial of this has to match this. So essentially, we're going to take the y partial of this and set it equal to this. So first we'll take the y partial. And if you want to, we can write this a slightly different way, which might make it a little bit more, might better capture the spirit of what we're trying to do. We're really saying we know that the y partial of this has to match and equal this. So this has to be x squared plus 3xy squared plus 2y. That has to happen. Okay, well, let's go ahead and take our partial. So this would be x squared plus, x squared plus 3x y squared plus, this is a function of one variable, so I'm just going to go ahead and say g prime of y. I'm not going to use the subscript notation because it's not a function of more than one variable. If you want to use a subscript notation, you can, just to keep it all uniform. That's up to you. Personal preference. Take your pick. So then here, this would be, well, just copy paste. We didn't have to do anything to this. Now look and see what cancels. We know this has to be true, so those cancel. These cancel. So let's move up here a little bit more. This tells us that the derivative of g has to equal 2y, which means that g of y has to be the integral of this, which is y squared plus c. So notice here that I did do the calc 1 method and put a plus c. Why didn't I have to put like a function of x? Because, right, if I differentiate this with respect to if I differentiate this with respect to y, wouldn't that be 0? So why am I not doing the thing that I just made a case for us having to do over here? Well, the difference here is this function f. This function f actually is a function of two variables. So we do have to take into account that other variable possibly being here. But what's different about this g? This g is a function of one variable. It can't have any x's in it. Like, definitively, we know there's no x's in it because it's a function of one variable. So that's why over here, we have to put the only thing upon differentiation of y goes away. Well, if x isn't an option and there's only two variables, well, it has to be c. It can't be y. If it were a y, then we'd have something else here. So this has to be a true constant. So now that we know that, we can again update or refine our potential. So what we would do is we would take our last best version of f and update what we found about g. We now know that g is y squared plus some arbitrary constant. So we can just do that to this. So this would be x squared y plus xy cubed plus y squared plus c. And what this is a general expression for all potentials of, capital F. What you'll notice in how a lot of these problems are phrased and how you see us, the instructors, do examples, these problems are all phrased by finding a potential function. So this problem, in a very specific sense and technical sense, is not asking for a general expression for all possible potential functions. We just want to know what's one of them. Just find one of them. Well, there's an infinite number of potential functions. Why an infinite number? Because since C is just a real number and there are infinitely many real numbers, that means there's infinitely many potential functions. If we just want to select one of these infinitely many, which one should we select? Well, it doesn't actually matter, but why don't we just pick the one where C is 0 to make our life easier? So most of the time, you won't necessarily see us writing this plus C here. We'll just go straight from this to this half right here. So underneath of this, I'll say a potential for F is f of xy equals x squared y plus x y cubed plus y squared. And that's a potential for F.